Hello everyone, I am Owen Rouille and I will talk about the computation of large asymptotics of three manifold quantum invariants. This is a joint work with Clément Maria. So, topology is a domain of mathematics that aims to recognize and classify objects up to homomorphism, that is, continuous deformation that do not involve cutting. The classical example of that is the transformation between a cup and a torus. And more precisely, we are focused on the subdomain of low-dimensional topology, that is, we are looking at three manifolds. In another word, 3D objects, or objects with intrinsic dimension 3. An important part of topology is the study of invariants. These are quantities that are preserved under homomorphism. Since homomorphisms are very complicated objects, these invariants allow to make the comparison between objects much easier. And a famous invariant, also the one we will be looking at for this talk, is the Turaev-Viro invariant. So this is a parametric invariant. While a bit hard to compute, it is powerful at distinguishing manifold, and it extracts information from the manifolds. This is shown or conjectured by Chen and Yang, which was published in 2018. So there is a parameter in Turaev-Viro Q that is fixed equal to 2 and that will remain equal to 2 during this whole paper. So we take a manifold M, we compute the Turaev-Viro of M for the other parameter R running over all odd integers, and we look at the sequence 2 pi over R times log of Turaev-Viro of M, and it is conjectured that this sequence tends toward the simplicial volume of M times some constant, and the simplicial volume is in itself hard to compute. So our contributions are twofold. To compute the Turaev-Viro invariants, a triangulation of the manifold is required, and we propose a method to compare triangulation to find out which one is the best to compute the Turaev-Viro invariant. And our other contribution would be the data generation. So we checked and extended this conjecture with using the previous contribution. The underlying objects we are studying are three manifold. They are three-dimensional extension of surface and they are represented by triangulations. For instance, here we have two tetrahedra. The edges are marked to allow identifications, and once glued together they will give a true manifold. The manifold we are considering in this talk are prime, closed, and orientable. The triangulation we consider are not necessarily simplicial complexes, they are generalized triangulation in the sense that a tetrahedra can be identified and glued with itself. For instance, here we have a generalized triangulation of the Mobius strip with only one triangle that is glued to itself. The notation we used are the V for the number of vertices in the triangulation, E for the edges, F for the triangles, and N for the tetrahedra. Two properties that will be useful later. For all triangulation, the number of edges equals the number of vertices plus the number of tetrahedra. And for any triangulation, whenever it's always possible to find an equivalent triangulation that represents the same manifold with only one vertex and the same number of tetrahedra or less. So now the art of the presentation, the definition of Turaev-Viro invariant. So Turaev-Viro invariant are colorings of the edges of the triangulations. So let's take another integer larger than 3, R, and the set of colorings is a set of integer and half integer between 0 and R minus 2 over 2. Now let T be any triangulation, and let us define the admissible triples. So 3 colors constitute an admissible triple if we have a triangular inequality between them, if their sum is bounded by r-2, and if the sum is an integer. That's the parity condition. That's the only one that is not linear. So now a coloring will be admissible if for any triangle in T the colors of the edges that composes that triangle constitute an admissible triple. And we denote ADM the set of colorings, the set of admissible colorings over T. So now the definition of Turaev-Viro is just the sum for all admissible colorings of the product of the weight of the faces. The weights that being a function that depend on the coloring and the face. So now some remarks. So the computation of the weights uses product of several sinuses. That plus the sum of all possible colorings. Computing Turaev-Viro is long and requires multi-precision arithmetics. In the worst case, there are r to the theta of n admissible colorings. And since Turaev-Viro relies on enumerating all colorings, it's a sharply hard problem. And I put there a remark towards the computation of Turaev-Viro. If the manifold we are looking at has trivial first homology group, then all the admissible colorings will include only integer colors. So we can discard the only nonlinear constraint. So now how to compute the invariant of Turaev-Viro. So first we have a backtracking algorithm that will just build the tree of all the colorings and go down the tree and print the branches, etc. We also have a fixed parameter tractable algorithm that will try to decompose the triangulation and use the tree width of the dual graph as a parameter. So here is the comparison between the two algorithms. So the parameterized algorithm is much faster in general, but it's much more expensive in terms of memory, and that's why we will focus on the backtracking one. As a short remark, so here is so against the R, the time needed to compute the Turaev-Viro invariant for some manifold. So green, red, and black are all the backtracking algorithm. Green is simple precision arithmetic, but it's not precise. We can use this one. Red is multi-precision, and we can notice 2 jumps because we had to increase the precision. And black is just too expensive, it's symbolic computations. And in blue, it's a parameterized one. To be noted here that usually the parameterized is faster. This manifold was just bad for the parameterized algorithm. And we couldn't go any further in our computations because at this point, the parameterized algorithm was filling the 128 GB of our memory. So now a few words about the software and the dataset we used. So all computation were done using the library Regina, which is pretty standard in the domain, and we had to add multi-precision arithmetic to it. Regina also provides a dataset of topologically distinct prime close-orientable tree manifolds. And actually it provides a census of all of them, all the different ones that admits triangulation with 11 or less tetrahedra. And this is what it looks like. So for instance, at 5 tetrahedra we have 31 different manifolds, 15 of them having a trivial first homology group. And 2 things to notice. The number of different manifolds explodes with the number of tetrahedra, and about half of them have trivial first homology group. Our first contribution is about estimating the number of colorings given a triangulation and the value for R. So first, this estimation is based on the Earhart polynomial. So if we take a polytope here in red, and it's scaling by a factor t, so the red shadow here, the function counting the number of integer points inside this scaled polytope is called the Earhart quasi-polynomial of the red polytope, and is a function that depends on the red polytope and the scaling factor. So it's a quasi-polynomial, but we won't go into the details here. So this quasi-polynomial is a bit hard to compute, so we will focus only on its leading term. So the degree of the polynomial is just the dimension of the polytope, and the leading coefficient is the volume of the polytope. Now, how to apply this result to our case? Well, we will take the computation of Turaev-Viro with r equal to 3 for a triangulation. So we take a triangulation, we take our constraint for r equal to 3. So we have ijk in 0, half, triangular inequality and the upper bound. And these three sets of constraints are all linear. This can be rewritten as I between 0 and half, etc. And we have a problem with the last one, which is not linear. So we'll just get rid of it, and we use the property we saw earlier. So if we take a triangulation with only one vertex on trivial first homology group, we can get rid of the last constraint, and we can build a polytope that is, so this polytope that will be in bijection with the admissible colorings. So this polytope is just a scaling of what we call the admissibility polytope given by these constraints. So now we use the Earhart theory to count the number of admissible colorings given a triangulation and a value for R. So Earhart gives us that the dimension of the polytope is also the degree of the polynomial, and we showed that this dimension is equal to the number of edges in the triangulation. So to ease the computation of the Turaev-Viro invariant, the first thing to do is to find the triangulation with the smallest number of tetrahedra. And this is hard. There is no way of unless apart from enumerating all triangulation. But random walk over the set of triangulation works well in practice. Then we need to look at the leading coefficient of the polynomial. So our dataset provides all minimal triangulation for the manifold, so we could just compare them directly. We didn't have to look for them. And the first question we asked ourselves was how much can we gain by minimizing this coefficient? So this graph gives, depending on the size of the triangulation, the distribution of the potential gain. For instance, here with the manifold that admits 6 tetrahedral triangulation, there is one of them that can gain a factor 1.5 in the number of admissible coloring by minimizing this leading coefficient. This is not a lot, although with the size of the triangulation, the potential gain increases, and well, computing the volume of the polytope can be done approximately very fast. The other thing we did was looking at the actual value of these volumes, and it gives us this graph. So once again, the size of the triangulation. So here for the 1 tetrahedra triangulation, and here 10 tetrahedra. And here are the value of the volume. And what we can see that is if we increase the number of edges, the volume of the polytope decreases, and this is in log scale, so it decreases geometrically. So what is the takeaway here? is that we gain a constant in the complexity of the computation. So it's we are more precise on the number of coloring we have to do. So now, are these prediction accurate? So here on this graph we have, depending on R, the worst prediction that was made for the triangulation with 1 tetrahedra, 2 tetrahedra, 3 tetrahedra, etc. And we can see that all these functions look like harmonic functions, and it is actually the case because what we're doing is actually a first order approximation of the number of vertices inside the polytope by taking only the leading term of the Earhart polynomial. And the other question is how bad or how good is the tree search, the backtracking algorithm. And for that we had a quick look at how many nodes of the tree was explored, divided by how many admissible colors are there. And so this is the distribution for all 5 tetrahedra manifolds, triangulations. And we can see that it converges and it's pretty low, so that's another thing to add to our conclusions, our observations. Now let's get back at our initial motivation, the conjecture of Chen and Yang. And to clarify, from now on we don't assume that the manifold we are looking at have trivial first homology group. So here is it again. So let's take a closed untable hyperbolic tree manifold M. Then this sequence, so 2 pi over r log Turaev-Viro of M, when r tends toward infinity, tends toward a constant times the superficial volume of M. So this conjecture had some success. It was extended, for instance, by Detchery, Kalfajani, and Yang. It was oriented to the not necessarily hyperbolic manifold, so closed oriented. And this time it's only the limit sup, but it's the same formula. And this conjecture has been proven for some specific cases. And so we were interested in verifying them, and since we are doing all the computation, we also had a look at the convergence rate of these sequences. So since we are looking at the convergence, instead of the sequence, we took the distance to the limit. And we looked at distributions, so it gives us whisker plots like this. So here we have the distribution of our sequence for all 6 tetrahedra manifolds. So it's a distribution for r equals 3, r equals 5, 9, etc. And here we have just the values. And to look at the convergence, we added regression with this function. So we minimize A and B to fit the data, red to fit the maximum, and blue to fit the median of the data. And and this result was already known, at least partially. So if we look at all 6 tetrahedra manifolds, they are all ciphered fibered manifold, and they fell in the second box here. And it was already proven by Detchery et al. That this was true. They even have the convergence rate, and hence this function. We took it because it fit and it was proven, but they did not have the inferior limit. So we have that, and we continued with manifolds that were not ciphered fibered. So when we are looking at small manifold with a small number of tetrahedra triangulations, most of them, if not all until 6, are ciphered fibered. So we had a look at non-ciphered fibered graph manifold with 7 tetrahedra. They are all here. and they exhibit the same behavior. So an argument in favor of the conjecture. We also work in the framework of Chen and Yang, so looking at hyperbolic manifolds, hyperbolic closed countable manifolds. And this time we did not look at the distribution, when we look at the values directly. So in green you have the limit for these two hyperbolic manifolds. This one has 90 Tetrahedra, this one has 10. So the sequence value are in blue and the regression is in red. We used another function here because we needed to include the limit, and we used harmonic regression because we couldn't go far enough to see a big impact of a regression with a log of x as opposed to just a over x. So just so a couple of words about this. This response took already a few days to compute, and going further would have taken months and months of computations for only a couple of points. So we really can do much better with these techniques. Another word about these graphs, and we can see the phenomenon quite well here, is at the beginning our curves, our regression, don't fit the sequence at all. This is because the dampening effect of the logarithm is very weak at the beginning. So the function 1 over r log of Turaev-Viro tends to smoothen the value of Turaev-Viro, and at the beginning a lot of manifold exhibit this chaotic behavior. That's why the beginning of the curve are not always so nice. If you are interested, we have in our paper many more graphs with these point clouds, regression, and limit. So I will finish this section by adding our own conjecture, and it's complementary to the other. So instead of the limit sup, we propose that the limit inf, the inferior limit, whenever we remove all zeros value, because some manifold exhibit periodic zeros in their Turaev-Viro sequence, and so when we remove these zeros, these things also tends toward the simplicial volume of the manifold times a constant. And we add that we can we have some other conjectures, for instance, about the convergence rate of all these sequences. So it's O tilde of 1 over r. We add the polylog factor because, for instance, with the hyperbolic manifold, we couldn't distinguish between both models. And now a few concluding remarks about the presentation. So we talk about the Turaev-Viro invariant, which is a powerful invariant but hard to compute. It also carries interesting information about the manifolds. Our first contribution was about predicting the number of admissible colorings in the computation of the Turaev-Viro invariant, given a triangulation and value for r. The takeaway message here is to minimize the number of vertices and triangle in the triangulation. We use this work to study and verify the conjectures for all manifold with triangulation with 70 tetrahedra or less, and hyperbolic manifold with 11 tetrahedra or less. We also checked the convergence speeds, and they appear to be similar. Further work on this would include studying the effect of characteristic of the manifold, such like their homologic groups, for instance, or the number of tetrahedra on the convergence speeds, and on the value of the sequence themselves. Thank you for watching the video, and hopefully see you at the conference.